Section 12.5 concerns lines and planes. Recall that when you did single variable calculus, tangent lines were a very useful tool, and we're going to have to figure out how to describe lines and how to describe planes in three-dimensional space. So our goals are going to be to give equations of lines, give equations of planes, and then we're going to be interested in the same kinds of questions you do in the plane. How do we find the intersection of two of these objects? How do we find distances between these objects? And so on. The first thing to notice is that slope-intercept form, which has served us so well for lines in the plane, is not going to describe a line in three-dimensional space. An equation like y equals mx plus b in two-dimensional space gives you the slope and the intercept of the line, but in three-dimensional space, there's a free variable. The free variable is z. So if you actually wanted to graph y equals mx plus b, you actually have all the tools to do that. You would draw the line y equals mx plus b in the plane, and then since z is a free variable, you would be able to extend that line above and below the plane in the z direction. Therefore, y equals mx plus b is not going to be a line, it's going to be a plane, like the one here in yellow. Since slope-intercept form won't generalize properly to three dimensions, we're going to need to think of another way of writing the equation of a line, and that's going to be the vector equation. So let's look at this line here. I've actually calculated, it looks like 5 points on this line, and the question is, what do their position vectors have in common? Well, let's take a look. Let's start with the point 3, 2, and then travel from 3, 2 to any of the other vectors. So for instance, we could travel from 3, 2 to the point 5, 1, or we could travel from 3, 2 to the point, what is this, 6.5, 0.25, or we could travel from 3, 2 to the point 9, -1, or we could travel back to the point 0, 3.5. And what you notice about these vectors is they are all parallel, which means they are all scalar multiples of each other. So, for instance, the vector to 5, 1 is the vector 2, -1, whereas the vector from 3, 2 to 9, -1 is the vector 6, -3. Remember that the vector between 2 points is just the difference of their position vectors. What that means is that for any point on this line, we should have that x, y, its position vector, minus the position vector of the point 3, 2, is parallel to 2, -1. Or another way we could write that is that x, y, minus 3, 2 is equal to some multiple t times 2, -1. And from this, we're actually going to be able to write a nice equation of which points x, y actually live on this line. We can write x, y equals 3, 2 plus t times 2, -1. And so using this equation, we're able to describe all the possible position vectors that live on this line. Where are these position vectors? Well, for instance, the position vector to this point right here can be thought of as the vector 3, 2, which is here, plus the vector t, and I don't know exactly what t is supposed to be here, times 2, -1. Remember, when we add these two vectors, which is what we're being asked to do here, we put these vectors head to tail, and then we go from the beginning point all the way to the end point. And so this is the position vector, 6.5, 0.25. By picking different values of t, we travel different distances along the line. With a negative value of t, we could even go backwards along the line in order to get this position vector. The idea is that by choosing the right t, we can get any point we want on this line. The great news about this approach is it's going to generalize to any dimension. This is called the vector equation of a line. What we need for the vector equation of a line is an initial point whose position vector we denote r0. This is the role of 3, 2 in the previous example. We also need a direction vector, which points in the direction of the line. This is the role of 2, -1 in the previous example. And then the formula, which should look like a generalization of exactly what we just found, was r of t equals r0. So this is 3, 2 plus t times our direction vector, which is 2, -1. R of t is our variable. It's our xy. T, again, can be any real number. Now that we have this vector equation, we can start to play around with the algebra a little bit. If we have r0, which remember is the position vector of just any point on the line, and v, which is our direction vector, ABC, then we can rewrite the vector equation by distributing the t to the ABC, and then doing the vector addition, and we get r of t equals x0 plus ta, y0 plus tb, and z0 plus tc. We can actually pull out the individual parametric equations that go with each point. The x-coordinate of the points on the line is always going to have the form t0 plus ta, or excuse me, x0 plus ta. The y-coordinate of points on the line is always going to have y0 plus tb. The z-coordinates on the line is going to have the form z0 plus tc. If we plug in different values of t, we get different x, y, and z coordinates of the points on the line. We're actually going to be able to graph these parametric equations in GeoGebra in order to figure out what a line looks like. Here's an example where we can practice using the vector equation of a line. So first, let's find the equation of a line through these 2 points. What do we need in order to find the equation of a line? Well, we need a point, and we need a direction vector. The point can be either one of the 2 points we've got here. I'll use the position vector of the point 3, 5, 2. The direction vector can be, well, since we have 2 points on the line, the vector that travels from one point to the other would be a vector in the direction of the line. So if we want to go from 3, 5, 2 to 1, 6, 6, then our x-coordinate changes by -2, our y-coordinate increases by 1, and our z-coordinate increases by 4. Putting this together, the equation of our line is r of t equals 3, 5, 2 plus t times -2, 1, 4. If we want, we can rewrite this as 3 minus 2t, comma, 5 plus t, comma, 2 plus 4t. Either form is correct. Where does this meet the xz plane? Well, recall the xz plane is where y equals 0. If we want y to equal 0, that means that 5 plus t, the y-coordinate of the line, has to be 0, and so t has to equal -5. If we want the x and y coordinates, we can just plug these in. So when we plug these in here and here, we get x equals 3 plus 10 is 13. We get z equals 2 minus 20 is -18. And so the coordinates of this point are 13, 0, and -18. Finally, does this line pass through the point 3, 8, -2? Well, it will pass through this point only if there's some t that we could plug in, such that the x-coordinate is equal to -3, the y-coordinate is equal to 8, and the z-coordinate is equal to 12. So, what would that t value have to be? Well, let's look at the x-coordinate. If we look at the x-coordinate, we get that 3 minus 2t equals -3. Well, that's fine. That has the solution t equals 3. Since this is the only t that could possibly work, let's try plugging this t in to the y-coordinate. For the y-coordinate, we want 5 plus t to be equal to 8. When we plug in t equals 3 here, we get 5 plus 3 equals 8. And that checks out. When t equals 3, the y-coordinate is what we want it to be. Let's try the z-coordinate, though. For the z-coordinate, we want 2 plus 4t to be equal to 12. We can plug in t equals 3 again, because that's our only option. And we get 2 plus 4 times 3 equals 12. 14 equals 12. This is false. So when t equals 3, the x and y coordinates are correct, but the z-coordinate is not correct. That means that this line does not pass through that point. Here's one final way to write the equation of a line. We can take the parametric equations, which looked like x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct, and we could solve each of these for t. What we'd get from the first one is that t equals x minus x naught over a. For the next one, we'd get t equals y minus y naught over b. And for the third one, we'd get t equals z minus z naught over c. Since all of these are equal to t, they must all equal each other. And so here's another way of writing the equation of a line in 3 dimensions. It's called the symmetric equations version, and we get this triple equation here, that all 3 of these quantities need to be equal. And if x, y, and z are such that these quantities are equal, then the point x, y, z lies on the line. So let's practice using this triple equation. How do we take this line, 3, 5, 2 plus t times 2, negative 2, 1, 4, and turn it into a triple equation? Well, again, we'd write the parametric equations. We'd write x equals 3 minus 2t, y equals 5 plus t, and we'd write z equals 2 plus 4t, and in each case we'd solve for t. We get t equals x minus 3 over negative 2. We'd get t equals y minus 5 over 1, and we get t equals z minus 2 over 4, and we'd set these all equal to each other. And so we'd get x minus 3 over negative 2 equals y minus 5 equals z minus 2 over 4. Does this line pass through 7, 3, negative 6? Well, all we have to do is plug in 7, 3, negative 6. And so we will get 7 minus 3 over negative 2 equals 3 minus 5 equals negative 6 minus 2 over 4. 7 minus 3 over negative 2 is negative 2. 3 minus 5 is negative 2. Negative 8 over 4 is negative 2. So the answer is yes.